Hello, and welcome to episode 3 of our grade 12 nuclear physics unit. Today we're going to take a look at types of nuclear reactions. Now we know about chemical reactions from grade 10. We know there are many different types of chemical reactions and they involve rearranging atoms in compounds. A nuclear reaction is similar, but it involves rearranging the nucleus of an atom. Now, this is something that chemistry does not deal with at all, but in physics, we can tinker with the energy levels required to mess with the nucleus of the atom. So we end up making new nuclei or changing the ones that are already there. Now, there are a couple of different types of nuclear reactions. We are going to be looking at 4 today, or well, 3, and there's 2 types of 1 today, but there are many others that are out there as well. So let's take a look. The first type of nuclear reaction that we're going to look at is called alpha decay. Alpha decay is when you have an element or an atom that decays and emits what's called an alpha particle. So alpha decay, and you may also see this as the Greek letter alpha, which looks like a little fish. So there's the Greek letter alpha. What we've got here is we might have a uranium-238 isotope here. So this is uranium. It has an atomic mass of 238, has 92 protons. Now this emits an alpha particle. An alpha particle is the nucleus of a helium atom. So in this case, what's going to happen is we're going to emit something and the nucleus of a helium atom. Now, with every single nuclear reaction, we must conserve a couple of quantities. Like chemistry must conserve mass, in nuclear reactions, we need to conserve the number of nucleons as well as the charge or number of protons, or overall charge. Protons does not need to be conserved, but the overall charge does. So, if I emit 4 nucleons, 2 neutrons, and 2 protons, these numbers here need to change accordingly. So what I'm going to have is I'm going to have 234 here, and I'm going to have 92 minus 2 is 90. So I have 234 plus 4 equals 238, 90 plus 2 equals 92. So here, I'm going to go take a look at my periodic table, and this works out to thorium. So uranium undergoes alpha decay to create thorium. Here's things you need to notice. Alpha decay always emits a helium-4 nucleus. This is sometimes written as alpha or 2 like that, or just an alpha. But this is the general pattern. I have something here, it emits an alpha particle, and then I have to figure out what's left of the original one. This is alpha decay. Now, alpha decay, as I said, emits an alpha particle, which is a fairly large, relatively for nuclear physics, particle because it's 4 nucleons. Beta decay is a little different. Beta decay, so here I've got carbon-14. So carbon-14 can undergo a beta decay reaction. Beta decay means it emits an electron. So an electron here has a charge of -1, and it is not a neutron or a proton, so it has a 0 there. We can actually write -1 here for the charge. So an electron, this here means that my carbon here is going to change. Instead of carbon, my number of nucleons stays the same. So I have 14 there, but this has to go up to 7. So this carbon turned into a nitrogen. So carbon-14 turned into nitrogen-14. And in beta decay, what's going on here is we also emit something called an antineutrino. An antineutrino is a little V with a bar over it to indicate that it's an antineutrino. This here is an almost massless particle. In fact, its mass is so small, we kind of ignore it in our calculations here because it's so tiny. And it goes very fast and basically doesn't interact with anything. We should know it's there because it does contribute to this. However, it basically runs on its merry way and doesn't interact with anything. So if you notice, alpha decay has a nucleus that splits off part of itself. It sends out an alpha particle, so the resulting nucleus is smaller. Beta decay has a nucleus where something in the nucleus changes. In other words, in this case, a neutron turned into a proton and squirted out an electron and an antineutrino. So beta decay, this first one here is called beta negative decay. There's the Greek letter beta. We refer to that as beta negative decay because we create a negative particle. Beta positive decay is similar, but the difference is we, instead of sending off an electron, send off a positron, which is an electron, but positive. It's the antiparticle to an electron. Yay, antimatter. So we also create a neutrino, not an antineutrino, just a neutrino. And this here is like a proton turning into a neutron. So I have 11 protons, which would be sodium, and I have a mass of 23. So my magnesium-23 underwent beta positive decay to become sodium-23. So this is beta positive decay. This here, beta negative decay, is also called electron emission. And beta positive decay is called positron emission. So electron emission and positron emission. You may recognize positron emission because it is used in medical scans for something called a PET scan, or PET, or positron emission tomography. So this nuclear reaction here is used in medical devices fairly commonly, actually. So one other thing to notice for these reactions, our charge as well as our number of nucleons is conserved as well. This is also written very similar to a chemical reaction where I have my reactants and my products. So this is what we start with, this is what we end with. Very similar. Alpha decay breaks off part of the nucleus, a little alpha particle, and sends it away. Beta decay is a proton changing into a neutron for positron emission, or a neutron changing into a proton for beta negative decay. Now, if I go take a look at our periodic table, what you may notice here is that there are a whole bunch of different isotopes that undergo different types of decay. So the idea with these different types of decay is that as we go through them, each isotope has a preferred method of decay. It's not the only way, but it is preferred. So if I, for example, take a look at carbon, you can see carbon-14 undergoes beta negative decay. If I go look at uranium, you can see that uranium-238 way down here undergoes alpha decay. You can also see that there are different types of reactions here. We've looked at alpha, beta negative, and beta positive. There are other types. There are proton emission. There's also spontaneous fission. So there are different types. We can also take a look over here. Sodium, for example, sodium-22 undergoes beta positive decay. Now, this actually makes a really interesting pattern. So if we look up something called a nuclide chart, This here is a graph of all of the nuclides and all of the isotopes that we know. On the y-axis is the number of protons. On the x-axis is the atomic mass. So if I zoom in here, and I can see if I go from neon to sodium, so if I go up on my y-axis, I'm increasing the element. If I go right on my x-axis, I'm increasing the isotope. I have oxygen 19, 20, 21, 22. Now, if I look down here in the bottom corner, I'm actually hiding it here. There's actually a key for this. And if I look, I can see anything here in yellow tends to undergo alpha decay. So I have this chunk here at the top of my periodic table that undergoes alpha decay. I also have this bottom half of my periodic table here, which undergoes beta negative decay, and here undergoes beta positive decay. So I've got a bunch of different types of reactions here. I've got my different types of decay modes that are useful for us. This graph here, I will put a link to this in the class notebook. This is a useful way to understand what's going on because we can see patterns. As I said, the yellow is alpha, and then these two colors are different types of beta decay. So you can see different elements have different patterns. Now, there's a third type of reaction which we should know about. Gamma decay is something where the nucleus of the atom doesn't change. What gamma decay is we have what's called an excited nucleus. So I've got a little asterisk here, which indicates that this uranium-238 nucleus is excited. What happens is sometimes something will undergo decay. So say an alpha decay happens, or say a beta decay happens, and it leaves behind a nucleus that's in a higher energy state than when it left. Just like electrons have different energy states, which you may remember from chemistry, those electron transitions, your nuclei of atoms have different energy states as well. When a nucleus decays, it needs to release that energy somehow, so it decays to its base state, 238, 92. It's the same stuff there, but it has produced a high energy photon. A photon here, this is a photon or a gamma ray. So a photon is like a little packet of electromagnetic energy. And in this case, it's in the gamma band. So it is very, very high energy. These gamma rays tend to be quite damaging, and they can cause all sorts of interesting effects. But what's happened here is this is not a particle. This is a little bit of light energy that is released at a very high frequency that can interact with other particles and stuff. So gamma decay, there's no nuclear change in terms of the number of neutrons or protons, but we do have it calming down effectively or becoming unexcited and releasing that extra energy as a gamma ray. Now, there are other types of nuclear reactions. There is also fission and there's also fusion, which we will take a look at later. But these are the three basic types of nuclear decay. I hope you have a great day. Thank you for watching.